You might already know that proteins are a fundamental part of your diet. But proteins aren't just nutrients you need for building muscles and running around. Proteins are much more interesting than that. However, before explaining what proteins really are and what they are made of, we need to talk briefly about one of my current favorite topics, molecular representation. You see, a protein is a molecule, which might not be evident to most people because molecules are usually represented like this or this. It turns out, however, that this diagram, aptly named a ribbon diagram, is one of the many ways to represent proteins. And look, initially I wasn't super happy with all of the freaking ways to represent the same exact thing. But when you consider that humans consistently use several representations for the same concept, and that proteins are so small they are literally invisible, or at least they challenge what visible is, then you start to understand the need for different models. Each model captures only some of the features of the molecule, but in the end they are all simplifications. In a ribbon diagram, you don't see individual atoms or the surface of the protein. However, you can see how a protein is a single chain that folds into a specific structure. The path of the chain is where the backbone of the protein is located. Side chains are attached to the backbone, but they aren't displayed in the ribbon diagram because that would obscure the structure. If you took the backbone, unfolded it, and labeled the different atoms in it, you'd quickly identify a repeating pattern. That's because the chain is actually a sequence of special molecules called amino acids, all of which share a common set of atoms that make up the backbone. There are 20 different amino acids, each with a side chain that has a different shape and different properties. Thousands of amino acids can combine to form a single chain, which, depending on its length and the order in which the amino acids are clicked together, can fold into different and unique structures. This folding happens because in the molecular world, everything is constantly jiggling, which exposes different amino acids on the chain to each other, allowing them to interact by attraction and repulsion, just like magnets. These interactions can make the chain fold into rigid helical shapes or smooth flat sheets, which can interact with each other too, resulting in a stable configuration, what we know as a protein. And the different properties of the amino acids and the incredible diversity of protein structures are what make it possible for proteins to play central roles in almost every biological process. Some proteins can attach to other proteins to build precise infrastructure. Others will identify and neutralize invading pathogens. Others will function like molecular factories and transform raw materials into finished products. And there are even proteins that can harvest energy from sunlight, which are the ones plants use during photosynthesis. Because yes, plants are full of proteins too. In fact, every cell in every living organism is full of proteins, and when an organism eats another, the proteins in the unlucky one will be split back into amino acids, which will then be recycled to create all sorts of new proteins for the lucky organism, including special proteins that will allow muscles to contract and organisms to move toward their next protein-rich meal. And of course, protein-rich meals are critical for people too. That's why, with the help of Tap for a Cause, we're supporting Action Against Hunger, a non-profit organization that's been treating undernutrition in children and their families in 45 countries for 4 years. Right now, Tap for a Cause will donate $1 to Action Against Hunger for every Minute Earth viewer who downloads their browser extension at tapforaCause.org/MinuteEarth2. That's in addition to the money raised for Action Against Hunger and other great charities every time you open a tab when you have the Tap for a Cause extension. Thanks, Tap for a Cause!